In this video, I will explain how a CALPHAD assessment works using the PARROT module in Thermo-Calc Software. The final goal of an assessment is a thermodynamic database, also called a TDB file, which includes the Gibbs energy descriptions of all phases in a system. The files we will discuss in this video are available for download at the links in the video description, so you can try using them yourself. The first step in an assessment is to search and evaluate the literature data. As a result, all the phases and reactions in the system are identified. Next, for each phase, a Gibbs energy model is defined depending on its crystal or chemical structure. Each Gibbs energy function contains some coefficients which are fitted to the experimental data later via least squares fitting. The result of this step can be saved to a so-called setup file. Then all the relevant experimental data are assembled in another file called a POP file. Finally, the coefficients of the Gibbs energy functions are fitted to the experimental data in the assessment step. The relevant file in this step is a work file, or so-called PAR file. I will now explain each step in detail. The experimental data that are used include the phase diagram data, such as melting points, invariant reactions, phase compositions, and areas of stability. As an example, let's have a look at the old phase diagram for the arsenic tin system. During this video, the assessment of this system will be explained. The phase diagram shows that, for example, there are two intermetallic phases in this system, arsenic tin and arsenic 3 tin 4. One is melting congruently, and the other forms through a paratectic reaction. Two eutectic and one paratectic reactions can be identified. However, we need more information, like the crystal structure of each phase, in order to define its Gibbs energy model, and thermochemical information such as the formation enthalpy, heat capacity, and so on, in order to have a consistent description of both the phase diagram and thermochemistry of the system. One example of such thermochemical data is the temperature-dependent heat capacity of the arsenic tin intermetallic phase, which is shown here in the table. Once we know the crystal structure of a phase, we can assign a Gibbs energy model to the phase. Two examples are shown here, the models of the liquid phase and the intermetallic arsenic tin phase. The liquid phase is a solution phase and modeled with only one sublattice. This means that both arsenic and tin components mix on one sublattice. The way that the phase description is entered in a setup file is shown to the left, and the corresponding terms in a Reddick-Kister polynomial is shown in the box to the right. The coefficients that are to be adjusted are V1 to V6. Note that not all these coefficients may be needed. One usually starts with V1 and V2, and more are added until a good fit to the excess energies is obtained. The second example is the model of the arsenic tin phase, which contains two sublattices. The first one is occupied by only arsenic atoms, but on the second one, both arsenic and tin can mix. As you saw before, for this phase there is heat capacity data. Thus, coefficients V20 to V23 are fitted to the heat capacity data. V18 and V19 are related to the enthalpy of formation of arsenic tin and its melting point. V9 to V12 are added to reproduce the solubility of arsenic on the second sublattice. As said before, the setup file includes the Gibbs energy descriptions of all phases, which themselves contain the coefficients to be adjusted. Once the setup file is created, we need to create another file which contains the experimental data. This file is called a POP file. Here, 4 examples of entering different experimental data are shown. The first example is how to enter the heat capacity data. The first line in each block is the command to create a new equilibrium. Then we set the status of the relevant phase, which here is arsenic tin, as entered. Next, the conditions according to the corresponding experiment are entered. For the heat capacity, the first time that we use it in the POP file, we need to define a way to calculate it by entering a function. Note that many thermodynamic functions, for instance enthalpy, are already defined in the software. However, the heat capacity is a derivative, and the first time that we use it in the POP file, we need to define it as a function of existing variables. Once the CP function is defined, we can enter the measured heat capacity under the given experimental conditions. We can add a label for each block so that later we are able to call equilibria in the block by their label. One can also use the command graphics to create an EXP file containing all the experimental data points once the POP file is compiled in PARROT. Moreover, one can add comments for each equilibrium block. The next block shows how the formation enthalpy is entered. There is more than one way to enter the formation enthalpy, but the way I have shown here is to fix the relevant phase. If you use this method, one less condition needs to be given. Another way to do this would be to set the phase status as entered and instead add a condition on the number of moles. We also need to set the reference states of the pure element to those used in the experiments. And the relevant experimental data here is the formation enthalpy. In the next block, entering a eutectic reaction is shown. In this case, all three phases involved in such a reaction need to be fixed. They are rhombohedral, liquid, and arsenic tin. This reduces the degrees of freedom to 1. Therefore, only one condition is required to be set. The final example is the congruent melting of the arsenic tin phase. The way to define the conditions here is to set the equal amounts of one of the components in the liquid phase and in the stoichiometric phase. In this case, the composition of tin is equal in both phases. In this slide, it was shown how the equilibrium blocks in the POP file are entered according to the experimental conditions. For more details, please refer to the Data Optimization User Guide of Thermo-Calc. This can be found from within Thermo-Calc in the Help, Online Help. Search for Data Optimization Guide, then click on Data Optimization User Guide. Once we have created a setup and a POP file, we are ready to start the assessment in PARROT. It is worth mentioning that we can also prepare macro files, also called TCM files, and EXP files in order to easily plot the desired property or phase diagrams and to compare them to the experimental data during optimization. During the assessment, first a work file, also called a PAR file, is created from a setup file. Then the POP file is compiled into the work file. Once done, we are ready to start the optimization, or in other words, adjusting the model coefficients. Very frequently, the phase diagrams and other properties are plotted during the assessment and compared with the experimental data. Steps 3 and 4 are repeated until satisfactory results are obtained. Let's run the setup file. It should be mentioned that the approach shown here is for pedagogical reasons. In practice, one can easily create a setup file from an existing TDB file. In that case, one still needs to add the phases and the parameters that are missing in the TDB file manually. Once these are added to the TDB file, a macro file is created from it, and then the macro file, called a setup file, is run in Thermo-Calc. But in this video, I will show how this is done using the commands line by line for new users. This is done in order to understand what each command in the setup file means. First, we go to the Gibbs module. We start by entering the elements arsenic and tin. The element descriptions are then amended using the amend element data command. Then we need to enter the Gibbs energy for each element in different states. An example of entering the reference Gibbs energy of arsenic is shown. We define this function as GHSERAS, and there are two temperature ranges for this function, this one and this one. These functions and all data for pure elements can be found in the Pure 5 database that is distributed with all Thermo-Calc installations. Next, it is shown how the liquid phase is entered. The phase name is given and then the number of sublattices, which is 1 in this case. Afterwards, the constituents of each sublattice are entered. The next step is to enter the interaction parameters for the liquid phase. The L0 parameter is entered and its relevant function is given. This continues until all elements, functions, phases, and interaction parameters are entered. Once we have prepared the setup file, we go to the PARROT module and make the work file using the command create new store file, or create for short. The next step is to compile the POP file using the command compile. We locate the POP file from the browsing window and then press enter several times. Then we go to the submodule edit. From there, we have access to the experiments. We can list all the equilibria and see a summary of the experimental data. In this submodule, we can manually add more equilibria, change the weights, and so on. Now we have a work file. It can be called from the PARROT module using the command set store file, or SSF. We start the optimization by allowing the variables to change. As you can see here, no variables are available to be optimized at the beginning. First, let's plot the phase diagram to see how it looks when all model coefficients or variables are 0. We start by fitting the heat capacity of the arsenic tin phase. The variables V20 to V23 are optimized in this step. We need to set some starting values for these variables using the command set optimizing variable. This is done to facilitate the fitting. Once the starting values are entered, we have to go to the Edit submodule to select the relevant experiment. First, we set the weight of all equilibria to 0, and then set the weight of equilibria related to the heat capacity of arsenic tin to 1, which in this case are numbers 1 to 30. Now if we look again at the list, we can see that all equilibria, except those relating to the CP of arsenic tin, are unused. We save and go back to PARROT. Then we run the optimization using the command optimize and set the iteration times, which in this case is 20. By listing the variables, we can see how the values have changed. We can also plot the heat capacity of this phase and compare it with the experimental data. Then I plot the phase diagram. We can see that the arsenic tin phase has now appeared in the phase diagram. This is repeated for the next stoichiometric phase, arsenic 3 tin 4. Now the two stoichiometric phases appeared, and you see how the heat capacity looks for the second stoichiometric phase. In the next step, the formation enthalpies of arsenic tin and arsenic 3 tin 4 phases are fitted. Let's see the plot of formation enthalpies now, and the phase diagram after these changes. Afterwards, the melting points and liquidus parameters are adjusted, and after this step, the phase diagram looks very close to the experimental data, and only fine-tuning of the variables is required. By the end of the assessment, usually all the variables are optimized together once or several times by using various weights on different datasets. A good practice for the final step of the optimization is to have all parameters rounded and only significant digits are kept. This was a simple demonstration of the assessment procedure in PARROT, which shows the main features.